I'm talking today about some work that I did with Joel Warman at Waterloo, Matt Hofferstein and Stevie Barlow at the University of Sydney, and Terry, who's not really anywhere at the moment, but was at Imperial. So that's the reference. Okay, so the first thing I want to talk about is what exactly do I mean by an assumption of non-contextuality? And I'm going to make this with, take us back to some classical physics, which is perhaps not the most natural setting, but it should hopefully illustrate the kind of thinking that I want you all to do about what one of these things is. Okay, so when we have some scientific theory, it presumably has some domain of validity where the predictions it makes are at least roughly correct.
Sorry to interrupt you. The video goes off if you
Okay. All right?
More or less.
Okay.
It's okay.
So, our scientific theories have domains of validity. And within any one of these theories' domains of validity, we tend to use summary statistics to refer to systems, which we can then use those summary statistics to predict how those systems behave. Often we don't want to use all the information about a system we have available to us. We don't usually want to take into account length contraction when we play snooker, or model tiger hunting behavior by trying to model all the chemistry going on in the tiger's body. Instead, we pick some variables which are illustrative of what we want to end up using and predicting, and then we use those, and we mostly discard the rest of the data. So I'm going to call such summaries non-contextual symbols, because within a particular theory, they encapsulate the necessary information about how that system behaves. And then our calculations depend only on these non-contextual symbols, but not on any other context. This is basically what I'm going to use as a definition of what one of these symbols is. So an example, perhaps a slightly trivial one, is that you might be working with some Newtonian gravitation, and you see people, you work in a lab, and you see people describing systems, and all the subsystems are labelled just by X, V, and M. And, no one's claiming that's a complete description of those subsystems, but you would hope that it encapsulates something, some physical properties, that these statistics you're using to calculate are actually, they reflect some behaviour at the ontological level. And ideally, you would want the behaviour at the ontological level to somehow explain your operational predictions. So we would hope that there would be some relationships that hold ontologically between systems described by the same symbol in this theory, or by similar symbols. So a sensible thing, a non-contextuality assumption then consists of basically three ingredients. The first one is an operational relation, which is a symmetric, reflexive relation over elements from operational theory, so these are things that we can do in a lab. Like we follow recipe A to prepare our system, or we prepare a system a different way. Then there's going to be an ontological relation, which again is symmetric and reflexive, and it's a relation over elements in the ontological model. These don't actually have to be equivalence relations. They don't have to be transitive. But these are some relationships that hold within the operational and then the ontological level. So a non-contextuality assumption then is just any statement that an operational relation implies something at the ontological level. It's a tool or an axiom that lets someone see some behaviour operationally and try and conclude something ontological. Okay, so for gravitation, someone might come up with a non-contextuality assumption as follows, that you have P1 and P2 here are preparations, and I will explain the notation a bit more clearly in a bit. And so you say that two preparations are related if they lead to systems with the same valuations of these particular ones. Here this isn't a complete relation, I'm not thinking about the velocity. And you might say, well, what does this mean at the ontological level? And of course it just means that the centre of mass of the thing is the same and the mass is the same. But nonetheless, this is a sort of conclusion of something ontological that one could make. That there's a sort of a hidden variable or a ontic state, lambda, which defines a mass distribution, and mass distribution has these properties. And this would be a good non-contextuality assumption because this goes some way to actually explaining the physical behaviour, what we see at the operational level. Okay, so briefly I will define the symbology I'm using, which is the framework of ontological models. it doesn't appear to be charging properly. Sorry. Obviously, because the projector is right.
Yeah, that's okay.
It's my fault. It's hopefully charging. Okay, so yeah, the ontological models framework. What is an ontological model? So the first thing is there's a set of allowable ontic states given by lambda. Then there's a set of probability distributions for state preparations. So this is saying that if you, and I am taking a slightly more quantum mechanical stance here, but if we prepare a state rho using some extra information alpha, so alpha just here would be any sort of contextual information, like are we realizing this this row, are we making it by half of an entangled state? What particular pure states are we mixing to make it? This could be any sort of contextual information. But hopefully in any sort of realist theory, when you perform this state preparation procedure, you get some distribution over real states. You don't necessarily always get the same real state, but there should be some distribution. Then there's also a set of transformations on the system which tell you when you do something like a unitary what happens to the real state, and measurement probability functions. So if we have a POBM element E, which we're realizing somehow, and we're in state lambda, what's the probability we get that outcome? Okay, so just a couple of quick examples of what these ontological models might look like. There's the Beltramitti-Bagansky or psi-complete model. So for a qubit, our state space is just a two-dimensional Hilbert space. When we prepare a pure state, you just get a hidden variable that corresponds exactly to the pure state. The unitaries are represented as unitaries. And when you measure something here, then you just get this trace as your probability for that measurement outcome to be seen. And so yeah, this is perhaps not a very interesting model, but it's something that does provide some ontology at least for quantum mechanics. Here's a slightly more interesting one called the Cauchy-Specker qubit model, which again has a spherical state space. But when you prepare a state, instead of getting 1 point, you actually get a distribution over the hemisphere, and theta here is the angle between the state you are trying to prepare, or the state you're preparing, and the position on the sphere that you actually end up getting. So you get like this cos theta distribution, so if you produce Z, you might end up with anything in the top hemisphere. Here, unitaries are represented as, basically you take an endomorphism from the unitary group into the rotation group on the sphere. So you just a unitary is just a rotation of the state space. And when you do a measurement, a pure state measurement, you see if you're in the right hemisphere. If you could have prepared that state, then you get that result. So, if I prepare Z and might end up with something over here, and I measure plus y and minus y, I would end up with the plus y1 because it's in the hemisphere corresponding to plus y. And so this is a slightly more interesting ontological model, and it has the property that if you know the real state, you don't actually know what pure state was prepared. Okay, so forms of contextuality then. So I'm going to talk a little bit about Leibniz's law, the identity of indiscernibles, which sort of says that if for all properties you could measure, x and y both have that property or don't, then you should treat x and y as identical things. And so this might, this is quite a powerful sort of deductive tool. I mean, and it's also one that people sort of hold to quite fast. So when people learn electromagnetism, they're often taught that the vector potential is not physical, it's not really instantiated. And the evidence given is just that you can have vector potentials if they differ by, I think, a curl-free function, then you end up with exactly the same statistics. And people are told, this is not a real object. They do not lead to single predictions, and therefore you should not consider this real. And also Einstein used this sort of principle in the derivation of general relativity by saying that you can't tell the difference between an acceleration due to accelerating and being still in the gravitational field. So in fact, we should come up with a framework where those things are ontologically the same. So then Rob took this approach and applied Leibniz's principle to QM, so bring this lens to the quantum regime. So in this language, we would relate two preparation procedures if they lead to the same density matrix, since that encodes all the information about the density about the preparation procedure, all the information about what measurement outcomes we can get. And then on the ontological level, we would say that you have these two distributions coming from these preparations are related if they are the same distribution. They lead to the same distribution over the ontic states. And so, and this is, an interesting proposition, and one that turns out that quantum mechanics is surprisingly reluctant to adhere to. And so, one thing I want to talk about, actually, is the main thing I want to talk about is trying to look at possibilities rather than probabilities and see how this affects how the non-contextuality assumption looks. So we define a new ontological relation where two distributions are considered related if they have the same support. So they may not assign the same probabilities to states or groups of states, but everything that's possible to get with one is also possible to get with the other. And I want to think about this non-contextuality assumption, that if you have the same thing operationally, then perhaps the probabilities aren't the same ontologically, but the possibilities should be the same. So this is a weaker assumption than the notion of non-contextuality I mentioned before, because we're not forcing on the ontological level such a strict relationship.
Sorry, is that probability distribution on what?
The ontic space, so the space of real estate. Okay, and this is basically called, this is basically Hardy contextuality. So, for example, I can show that quantum preparations are not Hardy non-contextual, and this is very similar to Hardy's non-locality proof, which is why I'm calling it this basically. So if I have these states, this is a slice, an equatorial slice of a Bloch sphere, you see that if I mix phi and minus pi over 2, I can make a state here. I can also make that state by mixing these two. So those are two very legitimate ways of making this state. And this connects to the non-locality case if this is the marginal of my half of the entangled pair, and if it's pure, I can be steered to one of this couple or one of this couple. So here's the claim under the Hardy non-contextuality assumption. Because I can make the same state by either mixing one of these two together, or by mixing these two together, whichever method of those two I use to make the state under the assumption should lead to the same set of states which is possible to build. And then if I just take both sides intersection with this support, well, this obviously cancels out, so we just end up with this. This one becomes this, just this intersection. And these two states can't have any overlap of their support because they're orthogonal states. So if there were a state that were compatible with each, then if I make pi over 2, I could make that state. And then that should be amenable to a measurement result of this. Because if it's possible to get it in that in that distribution. So I end up with the support of this state being a strict subset of the support of that state. But that is a contradiction, because anything in the support of phi could never measure the state orthogonal to phi. If I measure with respect to phi and its orthogonal state, then anything that I can get by preparing phi should definitely give me the phi outcome, which would imply that everything here could only give the phi outcome in that case. But we know that this is, this and this should have some probability of overlap. So an illustration of it is here. So if you carve the state space up into these different regions, so the top rectangle here is all the states that are compatible with pi over 2, and all the states at the bottom here, this is minus pi over 2. So they don't intersect because they're orthogonal, but there might be states in the middle not compatible with either. And then these two semicircles correspond to phi and minus phi correspondingly. Just by establishing this union, you can cross out sections which aren't in one of the two sides. And we see that all the states that we're allowed, for example, compatible with this, are also compatible with this. So we're not allowed to, So we're not even allowed to accept this weaker notion of contextuality for preparations in quantum mechanics. And obviously this sort of non-locality fueled Renato's talk just now. So perhaps we shouldn't be so surprised. But it does open the question of what assumptions can we weaken? There's lots of things that have been proven using non-contextuality assumptions. If we weaken our notion of non-contextuality, do these theorems still hold? Could we prove new versions of the theorem starting with weaker assumptions? Okay, so I'm going to introduce one other idea, which is this idea of possibilistic non-contextuality, which is a new operational relation to hold between this, preparation procedures and also equivalently for measurements and transformations, but I'm going to talk about preparation procedures now. So two preparation procedures are possibilistically equivalent if the supports of the density matrices they make are the same, which means that they would lead to the same possibilities in any quantum measurement, if not necessarily the same quantum probabilities. And so this is a non-contextuality assumption that I'm going to call a possibilistic non-contextuality. So we end up, if taking the different combinations of these ontological and operational relations, you end up with this square. So this is if we go from probabilistic non-contextuality to hardy non-contextuality, this is a stronger assumption to make than this one, because we are weakening our ontological relation. And if I go from hardy to possibilistic non-contextuality, that I'm also starting to make, this is a stronger assumption than that, because we have a looser relation operationally, so we might expect that we're going to relate more items and enforce this ontological restriction on more pairs. So there is literature about this sort of idea, but from this perspective it perhaps seems like it's not a very natural assumption to make. It's a bit of a mismatch between probabilistic and possibilistic contexts. However, they are actually the same thing for quantum mechanics, although this doesn't hold necessarily in every theory you could imagine. So if I have, clearly because this is stronger than this, if I have this, it implies this. So I just need to go the other way around. If we have two things that are possibilistically related, this means they have, when this would be 0, this would be 0, because that's what it means to have the same possibilities. They have the same kernel and therefore the same support, so they're supported on the same subspaces. So I can define this quantity, which is a density matrix. So this works in finite dimensions, because I'm assuming the existence of a minimum eigenvalue. So this quantity is a density matrix, and I can write rho naught, for example, as this convex sum. So I can make a legitimate way of making rho naught involves some amount of sigma 0 and some amount of rho 1, which means that the support for this is the union of these two supports, which is a superset of what I get for this one. But then, this is entirely symmetric, so I can write this equation down as well, and then I conclude that these two things are the same. So these really are the same sort of idea for quantum mechanics, although this idea where I subtract these two, you can't necessarily do in any ontological, rather any theory, because there's no guarantee. This is a quantum object because it fulfills all the criteria of being density matrix. But if you had a theory where you had a few more rules about what your states had to look like, then perhaps it might not work. So this does mean that the Hardy non-contextuality claim can be thought of as a weakening of Leibniz's principle. So if two objects give rise to the same operational possibilities, they realize the same ontological possibilities. And this does sort of meet the criteria for a good non-contextuality assumption because it explains itself. It's a motivational factor. This would say, if you have two objects in your theory, or operational theory, that you could never fully hope to distinguish, by which I mean there is no measurement you could make that with any probability would give you an outcome that would make you know that you'd had object 1 over object 2. Like they're not distinguishable with certainty. You could never absolutely get that knowledge. You can get Bayesian evidence that you perhaps had one system instead of the other, but that Bayesian evidence will never lead you to certainty. This would say that the reason you can never have that certainty about which system you have is because actually there's no certainty at the ontological level either. Even if you had access to the hidden state, you would not be able to work out with certainty which of the preparations had happened. So this does mean that this is a sort of strictly weaker Leibniz's rule, and therefore a motivational factor for some of this possibilistic non-contextuality like Hardy's theorem and these assumptions here. So, just a brief word about classical compatibility conditions and quantum compatibility conditions. So, Finkelstein and Mermin, when they're talking about a bunch of agents who each assign a quantum state to a system, they said that they considered state assignment consistent if in any measurement context, any measurement set you can do on the system, there would be some event that they all agreed was possible. And so a consistent set of state assignments is a set of density matrices with some overlap in their operational possibilities. So under an assumption of possibilistic non-contextuality, this reduces exactly to its classical case, where a set of state assignments for a classical system are consistent if there is some classical state they all agree to be in. It just becomes the same idea, but applied to an ontological model rather than a presumably accessible classical state. So an example of what that is if I roll a die and I can see a 2 on the side and I can't see anything else, and someone else can see a 4, then that's consistent because the 6 or 1 could be at the top. But if we saw, if a third person came along and said, oh, I saw 6 on one side, then that would be either the die would not be a standard one, or one of us would be wrong. It would not be a set of consistent assignments. And in Kay, Fuchs, and Sharp, they consider another set of quantum compatibility criteria. And the strongest one that they consider, they call equal support, where the rho I have the same support on the Hilbert space. And under this assumption, this also reduces to a classical concept, that of concordance, where a set of agents have all agreement on which states are possible for a system under consideration. Okay, so I briefly mentioned the idea of trying to reprove theorems under weaker assumptions. And one example of this is, I'm going to talk about psychostemic models under these possibilistic non-contextuality assumptions for measurements rather than for preparations, which I talked about before. So just briefly a cytostemic function model, rather, which I mentioned earlier. So it's an ontological model where the wave function isn't ontologically instantiated. So if you have a real state, you can't tell unambiguously which wave function it was compatible with. Wave functions share real states. So this is a very similar definition than the one you saw earlier. I'm just saying that two measurements that you can do in different measurement contexts, different outcome labels, are related if they lead to the same probability statistics, no matter what preparation you stick in. So no matter what preparation you measure it on, these two things lead to the same probabilities, so they're indistinguishable. And on the ontological level, two things are probabilistically related if they always lead to the same outcome probabilities, no matter which ontic state the system is in. So these kind of non-contextual models are cyontic, so they're not cytostemic. The wave function is ontologically instantiated as part of a real state, and that was proved independently twice. Okay, so a notion of non-contextuality for measurements, which is possibilistic, is very similar. We relate them if they lead to the same possibility at sign. Okay, so I'm going to try and quickly guide through the proof of a theorem that restricts how epistemic these models can be. So I'm going to find two sets called R and T. So R, for a measurement here, is the set of ontic states that, when measured with this POVM element, give that element with probability 1. And T is the set of ontic states that possibly yield that POVM outcome. So, and then the model is faithful if these sets are the same whenever two POVM elements are probabilistically related, which just means that it just depends on the POVM element and not how I do the POVM with a specific dilation or depending on what I measure alongside one particular POVM element. These sets are defined just by K. So a quick note is that these things are sort of possibilistic conditions. You can identify if something is certain, if in its contexts it is possible and nothing else is. And this is obviously just being possible. So these are both conditions that you can recognize possibilistically, and under a very modest assumption, this is true for possibilistic and non-contextual models. And so these sets are well defined. Okay, so the theorem statement is kind of nasty. If psi1 and psi2 are two states in a Hilbert space of dimension bigger than 2 to the n, and their square overlap is less than cos 2n 2 tan inverse 2 to the 1 over 2n minus 1, which is a function that goes to 1 and then goes to infinity, then in any faithful ontological model they have disjoint support, which means that the bigger the Hilbert space dimension is of the system, the bigger a bound there is on which states, how much overlap states can have and still have epistemic overlap. Because this is a psi-onticness condition because there's no overlap in the ontic distributions for these two states. Okay, so without loss of generality, I denote the states in this way, and we can do that because we can have a unitary operation that maps any two states with a fixed overlap to something like this with fixed overlap, and a unitary must respect ontic overlap. So if a state has if two states have an overlap, and you transform those states, then the states you transform those things to must have an overlap because something that was compatible with both states must still be compatible with both states. So if we consider a measurement indexed by some vector v in AV to the n, that means that on each of these qubits in this space, we either measure with respect to A, not A, or B, and not B on each of the qubits. So my claim is that if there's an overlap of these distributions, it's a subset of the R set for the projector onto the one of these with no bars on the top. And the reason for that is, let's say we have a 2-qubit system. So we have an ontic state that is compatible with AA and BB. So if I measure the first one with respect to A, because that qubit is in the support of A, it can't give me this one with a bar. And if I measure the next qubit with respect to B, again, I can't get the not B entry, I must get B. So it's in this case, I would say that psi 1 and psi 2 have, if they have overlap, that overlap is in the R set for ket A, ket B. And because it works for all these vectors, no matter which order I have these A's and B's in, it must be in the intersection of these R sets. So I then apply the construction on reality of the quantum state by P.C. Barrett and Rudolph to get a PVM where each of these PVM elements is orthogonal to one of these new states. And because these things have no overlap, they commute, and there exist PVMs containing both of them. So you end up with the R set for nu and the tracking set for pi nu being 0. And the reason for that is, if there were an ontic state that was in this and this, then when you measure this PVM, being in the R set for nu means that you get this outcome with probability 1. And being in the T set for pi nu means that you would get this outcome with non-zero probability. So this is a contradiction, and these sets have no overlap. And then it's just a little bit of set algebra where we so this thing is in this, which I said. So if you take an intersection of it with the whole state space, that also doesn't do anything. And this thing is equivalent to that, because the union of the tracking sets for all these pi ones must be the entire space. And the reason for that is when I do the measurement which contains all of them, I have to get some outcome. So every state must be possible to get at least one of these. Because if I'm in any state and I do this measurement, I have to get an outcome. So there has to be a possible outcome. And then these things have no overlap, and so you end up with nothing there. So this is not as strong a result as when you take stronger assumptions. When you take the stronger assumptions, you get a rather simple proof that everything's scientific. And this is not the proof that it's scientific, it's an bound on how epistemic the world can be. But nonetheless, it uses significantly weaker assumptions to prove this point. And so even if you hadn't accepted Leibniz's principle perhaps should hold for quantum systems, you might have thought that this weaker version would. Okay, that's everything. Are there any questions?